rockets. Your name is Elon Musk, and coolio, you just founded the company SpaceX. Wow. However, on the day of the big launch, you fall and hit your head on the counter. Oh no! Now you have to relearn all the fundamentals of rocket science. To do this, you decide to play the hit iOS app, Simple Rocket. But first things first, you're going to have to learn about Newton's third law. For every action, there's an equal and an opposite reaction. So, by burning rocket fuel, the rocket engine pushes exhaust flow out. In return, the engine is pushed upward. It's just a quick demonstration of how Newton's third law works in the rocket world. So, 3, 2, 1, launch. As you can see, we are gaining altitude. As fuel is burned and aimed towards the ground, the resulting action is that the rocket is sent upward by the normal force. Next up is the drag force. Before we get into space, we're going to have to talk about something in rocket flight that is extremely lame, and that's the atmosphere. Now, when you're in the atmosphere, you experience the drag force. It's a force that opposes the velocity of your craft, and as that velocity increases, the force of drag increases and wastes fuel. Surface area needs to be minimized in order to decrease this waste.
Alright, so we have a quick demonstration here. We're going to have two of the same aircraft with the same engine side by side. However, one has four weightless fuselages attached to it, while the other does not. And if you look in the top right-hand corner, you can see that the leftmost aircraft with no drag force, besides, the normal stuff, is going much faster than the one on the right.
Next up is gravity. This is another force that rocket thrust must overcome for the rocket to gain altitude. Gravity, in review, is a force between all objects that generally increases with an increase of mass and decreases at a greater rate with distance between the objects. For our purposes, however, the gravity we are worried about is the gravity between Earth and the rocket. Now that we're talking about gravity, we can finally talk about this map view. So let's stop accelerating upward. Now, we already have all of that momentum traveling up. However, we are accelerating towards the ground. Our acceleration is negative. So, as you can see, our trajectory is going downwards now. We are past the highest point that we were going to be sent towards, and so now we are plummeting towards the ground. Let's just speed this up a little. All right. And we're just gonna, just crash into the ground. So these are the three forces that we've got to worry about when getting into space: thrust, drag, and gravity. Now, drag is its own entity. It's going to lead to less fuel efficiency and just worse acceleration overall. But what we're really going to want to worry about, just for the fact of getting off the ground, is our thrust to weight ratio. So this is the ratio of the thrust force of the rocket to the gravitational pull on the rocket. Thrust to weight is directly proportional to the acceleration of the rocket, and thrust to weight must be considered when evaluating the number of rocket engines and fuel being used to launch, not to mention the drag that the surface area of those fuel canisters are going to cause.
Alright, to demonstrate thrust to weight, on the left we have low thrust, high weight from fuel. On the right we have high thrust, low weight. And as you can see, there is a very significant trade-off between having a lot of fuel but a low acceleration and having a low amount of fuel but a very high acceleration.
All right, next up we have the launch. So if a rocket that is launched just goes straight up, it will crash back to the ground and not go into orbit, unless it reaches escape velocity, but it probably won't. While the rocket is gaining altitude, common practice is to start initiating what's called a gravity turn for the rocket to gain both vertical and horizontal velocity. This will assist in getting into an orbit once we start later. It's finally time to send our craft into space. So, in 3, 2, 1, we have liftoff. So as you can see in the bottom right, our fuel is decreasing, but we are steadily gaining velocity. Around 5,000 meters, we're going to gain some horizontal velocity when we start our gravity turn. And let's go right about now. So if we look at our map, now we have some horizontal components to our trajectory. As you can see, our max altitude is climbing. We are almost out of the atmosphere on the max trajectory, and there we go. We're just going to let this stage burn off. All right, so now that we're out of fuel at that stage, we can go ahead and make those break off. All right, let's zoom on up there. And congratulations, we're in space. We don't have to worry about a drag force anymore, but we do still have to worry about the force of gravity. All right, it's time to learn some orbit basics. Once a rocket is out of the atmosphere, it has to increase its velocity parallel to the tangential of the planet's surface to get into orbit. Basically, what that means is it's got to increase velocity so that its horizontal motion increases relative to the Earth's surface, so it can create a semicircular orbit. We're going to call this burn a prograde burn. So an orbit can be modeled as uniform circular motion, as we learned earlier in the year, as v squared over r equals a, where a is gravity. Because a is gravity, it is going to be considered relatively constant. This means that if velocity is not high enough, the radius will have to be smaller to accommodate for it. And then that follows that if the velocity is not high enough, the radius will be too small and send the ship crashing back to the Earth. However, once an orbit has been attained, we no longer need to worry about crashing down to Earth because we are falling at the same rate that we are moving around the Earth. All right, so you heard what we need to do. What we have got to do is when we get up to our apoapsis up there, which is the max point in our orbit, we're going to add as much horizontal acceleration as we can. And this is going to allow us to fall towards the Earth as fast as the Earth curves away from us so that we go in a circle around the planet. Now remember, our tangential acceleration is the force of gravity, and we are increasing velocity to compensate for that and to create a radius that is a-okay and allows us to stay in that orbit. So we're going to go ahead and aim our rockets towards the prograde direction and go ahead and fire them off. I'm going to speed this process up a bit. So as you can see, our trajectory is expanding as we burn and add horizontal, and there we go. That's an orbit right there. All right, let's expand our view of the orbit. So as Kepler pointed out, an orbit is actually elliptical. So one of the foci of the orbit is the Earth's center of mass. And I find it easier to think of the loop of an orbit as a roller coaster. So as the train goes up the loop, it loses velocity. So right at the top, it's at its probably lowest velocity. But then when it gets to the bottom, it's probably at its highest velocity. Since velocity's magnitude changes, the motion is not uniform, and so an orbit more closely resembles an ellipse than a circle. Just like a roller coaster, there is a point where the satellite's velocity in an orbit is at a minimum, called the apoapsis, and where velocity is at a maximum, called the periapsis. Thank you for the comment, Caleb. You can see Our orbit is not circular, and that's what Kepler meant by how orbits are actually elliptical. So as you can see, our periapsis, the lowest point in our orbit, but also the point where our velocity is the highest, is at about 1/5 of the altitude of our apoapsis, where altitude is going to be the greatest, but velocity is also going to be the least. And so we can think of this like that kind of roller coaster loop. The apoapsis is the top of our loop, where the periapsis is the bottom of our loop. And so we are just stuck going in that loop forever, gaining velocity and then burning it back up to get up to the apoapsis and then falling back to the periapsis again. All right, here's how we use an orbit. So remembering our v squared over r model, we can increase the radius of our orbit by increasing velocity. By adding velocity at one end of the orbit, we create a new sort of bottom to our loop, where velocity is at a maximum at the periapsis. This means a new opposing apoapsis with a minimum velocity will occur opposite the periapsis. But when we increase velocity at the periapsis, that's going to cause an increase of altitude for the apoapsis. Because the force of gravity decreases as radius increases, eventually the acceleration in the v squared over r equals a model will not be able to accommodate for a large velocity with a corresponding large radius. This is called the escape velocity. All right, so we're going to be shooting for the moon today. And how we're about to do that is that we're going to add velocity at one point in our orbit. It's basically going to be where our periapsis is right now, but it's going to be a little off. What that's going to do is aim our apoapsis and extend it so that it crosses into the moon's orbit, and hopefully we enter into the moon's sphere of influence with its gravitational force. So let's try that out. Let's get a little bit farther down in the course of our orbit. Right there is probably good. Oh, and it looks like we're out of fuel. So we'll make a new stage and then fire off our rockets and speed her up. All right, so you can see that our apoapsis is going to increase altitude at an increasing rate until eventually we want it to just barely kiss into the moon's orbit. That looks good. And now let's go towards the moon.
Ooh, this is gonna be close. We got it. All right.
There are also several different types of orbit. So you can describe an orbit as having an eccentricity, and this describes how ideal to a perfect circular orbit an orbit is. So an eccentricity of 0 describes a perfect and unobtainable circular orbit. An E value, which is eccentricity, between 0 and 1 describes an elliptical orbit as Kepler described. Now, once you get past 1, the orbits are typically escape trajectories. So they're not actually completing an orbit around the planet, but rather they are graphs such as parabolas or even hyperbolas as you get to higher energy values. So what that is a path that goes into the planet's sphere of influence and then goes straight back out, and it's either going to follow the parabolic path or the hyperbolic path. All those conics that we learned in math class are finally paying off. All right, so back to our moon rocket. As you can see, our trajectory is heading right towards the moon. We're going at about 788 meters per second, which is probably more than enough to escape the moon's velocity. So what we're going to do to get out of this situation is burn in a direction that makes us go around the moon. So let's just fire our rockets over there. As you can see, our trajectory is going, hopefully, there we go. So as you can see, This probably looks like a hyperbolic, maybe. It also might be a parabolic. But if we speed up towards that kind of center area of that orbit, and then do a retrograde burn, and retrograde just means the opposite of prograde. This is going to decrease our velocity. So now we're decreasing the velocity of our orbit, making it bend back around, and actually we decreased a little bit too much. So let's go this way. All right, this looks a little more parabolic now. And so yeah.
All right, thank you for coming out today, Mr. Musk. I hope you learned a lot. See you later.